plate heat exchanger model HE200 has been designed to allow students to get familiarized with the operating of plate heat exchanger and to collect the necessary experimental data for the calculation of heat losses, heat transfer coefficient, log mean temperature difference, and etc. Students will also be able to study the effect of flow rate on the heat transfer rate. Later, students may apply this knowledge to complex industrial plate heat exchangers.
So my name is Yu. Now we are going to start the first step for the experiment, which is the general startup procedure. So first of all, we're going to do some inspection to check whether the equipment is in good condition or not. Next thing, we need to make sure that all the valve is closed, and we're going to fill up the cold tank. And next, we need to fill up the hot tank over this part. So now we're gonna turn on the main switch and we will turn on the heater button, and for this right we will control the temperature using the temperature controller. So by controlling it, we will press this button and we will set the desired temperature. So this
All operating instructions supplied with the unit must be carefully read and understood before attempting to operate the unit. Always check and rectify any leak in the system. Do not touch the hot components of the unit. There are many safety precautions and maintenance, such as the following. First, the unit must be operated under the supervision of trained personnel. Second, always make sure that the heater is fully submerged in the water. Third, be extremely careful when handling liquid at high temperature. Fourth, always switch off the heater and allow the liquid to cool down before draining. Fifth, restore the system to operating conditions after any repair job. Sixth, only properly trained personnel shall be allowed to carry out any servicing. Manufacturer's manual must always be observed. Lastly, before servicing, shut down the whole operation and let the system to cool down.
Hi, my name is Alia Batisha and we will begin our experiment 38 counter current plate heat exchanger. To begin, the first procedure of our experiment is to start the general procedure as presented by Yong in the So for the third step, we need to switch on pump 1 and pump 2. For the fourth step, adjust valve H1 to obtain the desired current for hot water streams. And adjust valve H4 to obtain the desired current for cold water streams. The fifth step is to allow the system to reach steady state after adjusting the valve for about 1 or 2 minutes. So the sixth step is to record the temperature 1, 2, 3, and 4. So the seventh step is to repeat step 4 to 6 for different combination of fluoride F1 and F2. And next, so the eighth step is to repeat steps 1 to 7 for different hot water inlet temperature. So the last step of our experiment is to shut down all the equipment.
Hi everyone, I am Nurbalqis and I'm here to start the 13B co-current plate heat exchanger experiment. Now let's start. Number 1, we need to perform the general startup procedure as the Yonghenju mentioned before. Then we have specific valves that need to be opened and closed. For example, HB7 needs to be opened like this. For the third step, we need to switch on the pump 1 and pump 2. For the fourth step, we need to adjust the HB1 and HB4. HB1 is a hot flow rate. And we need to adjust HB4 for the cold flow rate. Now, the fifth step is we need to record all the temperatures for the inlet and outlet. For the first one is 51, 52, 53, and 54. Okay, for the next step, we need to repeat step 4 until step 6 for the different flow rates ST1 and ST2. And then, we need to repeat step 1 until step 7 for the different temperatures. And for the last step, we need to shut down the plate heat exchanger.
Now we are going to carry out the last procedure, which is the general shutdown procedure. So first of all, we will turn off the heater, and then we will turn off the P1, the pump 1, also P2, the pump 2, and we will switch off the main switch, and lastly we will close all the valves. So this is the last step for the experiment.
From figure 1.1, it is shown that heat loss increases as the volumetric flow rate of hot water increases. This is consistent in both countercurrent and co-current heat exchangers. As the volumetric flow rate of hot water increases, the amount of water in contact with the plate is greater. As such, more heat is lost to the plate. Next, according to figure 1.2, the efficiency of the heat exchangers remain relatively constant. Theoretically, the efficiencies of the heat exchangers should decrease with increasing flow rates. So, this discrepancy could be because the flow rates used were not high enough to warrant a greater change in efficiency, or some errors could have been done in the experiment. For figure 1.3, the overall heat transfer coefficient increases with flow rate. As the heat transfer coefficient increases, the heat transfer increases. This matches the data from graph 1.1 where heat loss increases. For this experiment, the flow of the hot and cold streams is set to counter each other. From diagram 1.4, as the volumetric flow rate of hot water increases, the overall heat transfer coefficient increases. This is shown to be similar to the simulated data obtained from ICON. The plate coefficient of hot flow also increases with volume flow rate as shown in figure 1.5, while the plate coefficient of cold flow remains constant. The temperature efficiencies are shown in figure 1.6. For this experiment, the flow of the hot and cold streams is set to flow parallel to each other, which the direction of the stream is the same. From diagram 1.7, as the volumetric flow rate of hot water increases as the overall heat transfer coefficient increases. This is shown to be similar to the simulated data obtained from the icon. The temperature efficiencies are shown in figure 1.8. The plate coefficient of hot flow also increases with the volume flow rate as shown in figure 1.9, while the plate coefficient of cold flow remains constant. After conducting and completing experiment 13, plate heat exchanger, we are able to collect the necessary experimental data to calculate the heat loss, heat transfer coefficient, log mean temperature difference, plate heat coefficient, and etc. We are also able to study the effect of flow rate on heat transfer rate, and this knowledge is applicable in complex industrial plate heat exchanger. The plate heat exchanger is operated in counter-current and co-current mode. In conclusion, counter-current flow plate heat exchanger has the higher overall heat transfer coefficient and efficiency compared to co-current flow plate heat exchanger. It is because more uniform temperature difference between hot fluids and cold fluids. Thus, this proves that counter-current operation mode of plate heat exchanger is more efficient because of the higher overall heat transfer coefficient and efficiency, which allow more efficient thermal heat transfer between two fluids in the heat exchanger.